The speaker tonight, David Kring, went to Indiana University and also got a Ph.D. in planetary geology from Harvard University. He has been involved with the Chicxulub impact crater. He has not only been involved in the early discovery of it, but in understanding the significance of it. Dr. Kring has been very involved in public outreach. Some of you may have seen him on PBS or the History Channel or the Discovery Channel. And I'd like to ask everyone here, when you hear his presentation in a moment, to be thinking of some questions, because he's indicated that he'd be very willing to entertain questions at the end. And I think that it would be a wonderful chance to have the opportunity to ask him some questions. And then lastly, Dr. Kring has an asteroid named after him. How great is that? So Dr. Kring, David, would you please come on up? Welcome to the HBS. We're delighted to have you here.
Geologists in the room, you know, most of the geologic history of the Earth, the first 500 million years, has been destroyed. And so we actually have to turn our attention to the moon if we're going to understand those events. Right at the cusp of when the geologic record begins to be preserved, we have on our planet the origin and early evolution of life. And so I'm going to try to weave together a story that talks about what we have learned from the moon, what it tells us about the early Earth, and from that, some hints of how life actually may have originated on our planet. Okay, so let's go ahead and move forward and have a couple of slides on how we go about deciphering lunar history. And the first way we go about this is using telescopic or orbital methods. This is either telescopes like in West Texas or in the Catalina Mountains outside of Tucson or in Hawaii. And if you look up at the moon using these telescopes, you can use the geologic principle of superposition. You can see one type of geologic unit on top of another geologic unit and infer from that the sequence of geologic events. And that's that first bullet that you see there, using the stratigraphy of overlapping impact ejecta blankets and lava flows to decipher the sequence of geologic events on the moon. We have a second technique that we use on the moon, and that is using the relative densities of impact craters on the surface. And this image of the moon that you see down here, which was taken from a telescope outside of Tucson, illustrates both of those methods. Here we have a basaltic lava flow that is flowed on top of these north acidic rocks, and so you know that this is younger than the part of the lunar surface. And using crater density, you can establish the same relative sequence. There are almost no impact craters on this surface, and there are thousands of impact craters on that surface, also telling you which is younger and which is older. Geologists use that to put together a stratigraphic column with the older rocks on the moon down at the bottom and the younger rocks at the top. And you can see, for comparison, the relative ages that we have on the Earth. This is, as all geologists know, a relative time scale until we can actually begin to put some radiometric ages on it. So that then brings us to the other way in which we can infer geologic history of the moon, and that is from a surface perspective. Fortunately, for those of us in this country, we had a very exciting series of missions. We sent 6 crews to the lunar surface during the Apollo program, and the astronauts, like Jack Schmitt here, collected those samples, carefully selecting them, and then brought them back to Earth, where geologists such as my advisor and myself have continued to analyze them. Here are a few examples of what these rocks look like in thin sections. Many of them are impact-derived rocks, providing a picture of the impact cratering history of the moon. And that's really going to be the focus of this evening's presentation. But I'll try to give you all of lunar history. With these samples, we can provide absolute ages using radiometric techniques. And I have to say that something always to keep in mind when we talk about different ways of studying a planet or planetary surface like the moon, and that is the value of samples. The samples that the Apollo astronauts collected was nearly 50 years ago, but with new ideas and new analytical techniques, we can always go back to those samples and learn some exciting new things. And in fact, in one of the slides that you saw looping as you were walking in, there was actually a little story in the corner about how just last week we were able to discover, using new analyses of lunar samples, that the water in the lunar mantle was derived from asteroids and not comets. And so sample returns, which is something that I'm advocating that we do again, is exceedingly important. Okay. Now, about 10 years ago, we were going back to the moon, and in fact, if we had stayed on the trajectory that we were on at the time, we would have had astronauts around the moon last year. And I have to say, what a different world we would have if the astronauts had been back at the moon last year. At that time, NASA went to the National Academy of Sciences and the National Research Council, and they said, if we in fact do send crew back to the moon, what is it they should be doing? And there was two parts to this question. First, review what it is we've learned from the Apollo program, and based on that knowledge, decide what it is we should do when astronauts return to the surface. This is the name of that report, The Scientific Context for Exploration of the Moon, and I'm going to highlight a few of the items in that this evening. This report outlines some major science hypotheses and concepts that evolved, as I said a moment ago, from Apollo. The first of the big ideas that emerged from Apollo and the post-Apollo era is the idea that the Earth and the Moon formed in the midst or as a product of a giant impact. So there was a proto-Earth and then an object roughly half the size of the proto-Earth that hit, and that threw up debris that went into orbit around the proto-Earth, and from that disk of debris, the moon eventually accreted. Here's a movie that a good friend of mine, Robin Canuck, made. She works at the Southwest Research Institute. That shows that impact event, and you'll see that the impactor and the Earth are largely melted and vaporized. Most of the impactor goes into a disk of debris that is in orbit around the Earth. Some of that clumps together into little moonlets. Most of those little moonlets continue to accrete to the Earth, and then the distributed dusty-looking material that you see remaining in that simulation is what eventually does accrete to form the moon in about 1,000 years. It's a very quick geologic process. Now, when that finished, the moon was very, very close to the Earth. You can see here, this is the Earth, and there's the moon, just about 15,000 miles above the terrestrial surface. And so the moon was 16 times larger in the sky then than it is today. And so to give you a sense of that, here's the moon today, and here's to the same scale what the moon looked like in the Earth's sky at that time. It would have been a completely different looking sky. The moon, of course, over the last 4.5 billion years has been moving away from the Earth, and today is about 60 Earth radii from our planet. The other big idea that evolved from the Apollo program and needs to be explored in more detail when we go back is something called the lunar magma ocean hypothesis. As you saw in the preceding slide, the Earth was a molten mass, as was the moon following the giant impact event. From just a couple of anorthositic nuggets in the soil at the Apollo 11 landing site, my advisor John Wood and J.B. Smith determined that the moon, when it cooled, was initially a magma ocean, and when it began to cool, olivine pyroxene settled to form a mantle. Then plagioclase began to crystallize, and it being less dense than that melt floated, and that has formed the bright white highlands that you see in the ancient part of the lunar surface today. Putting all of that together, the sequence of events that we have for the moon is there was the magma ocean, which crystallized. As it crystallized, denser olivine and pyroxene sank. A northosite floated to the top, forming this crust. Afterwards, magmatic intrusions rising up from the mantle continued to intrude the crust. Eventually, basaltic lavas erupted onto the surface, producing those dark basaltic plains that I pointed out in the first slide. And throughout that series of events, impact cratering was continuously modifying the surface of the moon. That then brings us to the third big idea that emerged from the Apollo program, and that is the idea of a lunar cataclysm. And what my group has subsequently shown is in fact an inner solar system cataclysm. That is, the surface of the moon was intensely bombarded, as was all of the terrestrial planetary surfaces in the inner solar system. And that's going to be the idea that we explore with the rest of our evening. Okay? So how did we come upon this hypothesis? Well, there's two ways to analyze the samples that Jack Schmidt and others brought back. One is to take the impact melt bridges and simply determine the radiometric ages randomly. Just take all of them that you can get and start plotting them. And so here's a diagram and histogram of the number of samples as a function of their age that was determined. This is from 4.4 billion years ago to 3.6 billion years ago. Here's a series of argon-argon ages from Apollo 14, argon-argon ages from Apollo 16 samples, the same from Apollo 17 samples, and then some rubidium-strontium ages from all of those different missions. And what you'll see is there is a pileup or a spike of ages around 3.9 to 4 billion years ago. That was seen, as you see here, in the argon, and rubidium radiometric systems. It was also seen in the uranium-lead system, and from that, the hypothesis emerged that the moon was intensely bombarded at that point in time, 3.9 to 4 billion years ago, producing all of these impact rocks with all of these ages. And that the term was coined the lunar cataclysm hypothesis. Now, another way of getting a handle on the flux of impact events early in lunar history is to try to connect specific samples with specific impact basins on the lunar surface, okay? And so let me introduce you to a series of 15 or 17 of these basins. These are in stratigraphic order, so Nectaris is the oldest in this sequence. The very last of the giant basins on the moon is called Orientale. The first thing I want to point out is the size of these basins. Okay, so the second column I have the diameter. The smallest of these is a little over 300 kilometers in diameter. The largest of these is 1,200 kilometers in diameter. And for some of you, you're thinking, well, what do these numbers mean? Well, I just want to point out that Chicxulub, the dinosaur-killing impact that wiped out most life on the planet Earth 65 million years ago, was a puny 180-kilometer crater. And so you can imagine the calamity that these large impact events were producing. Now, we have a couple of samples that we think were produced by these basin-forming events. We have samples from Apollo 15, which landed on the edge of the Imbrium Basin that we think tells us that that basin formed about 3.85 billion years ago. Apollo 17 landed on the edge of Serenitatis Basin, and we think we have a couple of samples there that date to about 3.89 billion years ago. And we have some hints that Orientale was produced 3.8 billion years ago, and Nectaris, the oldest of them, was produced about 3.9 billion years ago. And so if you look at that range of ages, you realize that all of these impact events were occurring in a very small amount of geologic time, hence the term the lunar impact cataclysm. Okay, but you can see we only have two ages that we're comfortable with, a couple of question marks, and nothing about these ages in between. And moreover, this is only 1/3 of the impact basins that were produced on the lunar surface. We have absolutely no information on the ages of the other 2/3 of the basin-forming impact events. Okay. If we put that together schematically, I'm plotting here a flux of impacting asteroids and comets. So it's increasing vertically, as a function of time. This is 4.5 billion years ago, and here is today. Of course, soon after the Earth and the Moon formed, there was a lot of impact events as the planets continued to accrete debris from the early solar system. And then that flux of impact events fell off. And then based on Apollo samples, this idea emerged that there was a spike. There was some enhanced flux of material about 3.9 billion years ago, which we refer to as the lunar cataclysm. Now, for the astrobiologists, or the people interested in the origin of life, this is really interesting because it immediately precedes the earliest isotopic evidence of life on Earth about 3.8 billion years ago, and of course it begs the question, did this have something to do with the emergence of life, or had it in some way stifled the emergence of life until this point in time? And I'll return to that later in the talk. Okay, now, based on the Apollo samples, which were, you have to understand, collected from very small areas on the lunar surface, for purposes beyond testing the lunar cataclysm hypothesis, there is still some uncertainty attached to this. What we can agree on in the lunar science community is that the basin-forming epoch seems to have ended about 3.8 billion years ago and is potentially a factor in the origin and early evolution of life. But what's still debated is what is the magnitude and duration of that cataclysm, which will greatly affect our assessment of its effect on the origin of life. And we also still debate what happened between 4.5 billion years ago and 4.1 billion years ago, what the source of the impactors was, and what the effects of those basin-forming impacts events were. Okay. So here is a little movie that puts together that history as I've just outlined it, and I'm not going to say another word until this is over. Okay, so that's the picture of the moon that we have today based on what we were able to infer from Apollo. Now you might ask, what is the source? In fact, I addressed that question a moment ago. What was the source of the debris hitting the lunar surface? And this is a question that my group's been trying to address for the last 15 years, and we've been able to determine that most of the impactors hitting the moon were from the asteroid belt. And this is a little graphic that illustrates the distribution of the planetary bodies prior to the cataclysm. Here we have the Earth and the Moon. There are a few leftover objects, impactors, in the vicinity of the Earth and Moon system. These are leftovers from the accretional process. Then farther out from the Sun is Mars. Then there is the asteroid belt, which was bigger and more massive than it is today. And then, of course, we have the giant planets, Jupiter and Saturn, and then Uranus and Neptune. What we've been able to deduce is that the impactors that hit the moon have the geochemical signatures of asteroids. We've also been able to infer that the size distribution of the asteroid belt was perfectly sampled. That is, we had the same proportion of small impactors hit the moon as large ones. The only way we know to cause that to happen is for gravitational resonances to sweep through the asteroid belts. Today we know these as the Kirkwood gaps. Today they're fixed in space, but based on our studies of the moon, we've inferred that they moved 3.9 billion years ago. If the resonances moved, then Jupiter had to move, okay? And so let me flip back and forth between those two slides. This is before the cataclysm. Jupiter moved, the resonances swept through, and threw a lot of asteroids at the moon. So this is what we infer happened 3.9 to 4 billion years ago. We can say, based on the geologic record, that Jupiter moved. We're still debating what caused Jupiter to move, and that's the topic for another talk. Okay, so all of that was captured in this report back in 2007. It outlined these hypotheses, and it tried to provide some direction for what to do next. This report identified 35 specific investigations, and importantly, the report prioritized those investigations, and the highest science priority is to test the lunar cataclysm hypothesis, in part because it completely resurfaced the moon and because of the implications that it had for Earth and the origin of life. The second highest priority was to determine the age of the oldest and largest basin on the moon, which is called the South Polacan Basin. If we can determine the age of that basin and the ages of any of the younger basins, then we'll be able to answer the question about the magnitude and duration of that lunar cataclysm. Okay, so our group down in Houston took this report and asked the question, where on the moon can each of those 35 investigations be addressed? And we had tried to address this question very objectively. We tried with each question to identify absolutely everywhere on the lunar surface you could address it. As you did this for every question, we generated geologic maps, and then we stacked these maps. And when you stack those maps, you realize that there were certain locations on the moon where you could address a huge amount of science. And so those became our prioritized landing sites, which we captured in this report called the Global Lunar Landing Site Study. This is a monster, I have to say. It's about 688 pages, not the type of thing that you want to read before you go to bed. But it has been very instructive, and it has been guiding the research, the exploration activities of the lunar surface that NASA and other space agencies have been doing for the last 5 or 6 years. Okay, based on that report, we determined that the Schrodinger basin on the lunar far side, which is inside the South Polacan Basin, the largest basin on the lunar surface, is the highest priority landing site. Okay? If you go to Schrodinger Basin, you can test the lunar cataclysm by determining the age of one of the youngest basins as well as the age of the oldest, the South Polacan Basin. So you get both the highest and the second highest priority goals, and you can also address 23 of the 28 remaining goals. So it is a scientific hotspot, if you will. Okay, so at that time, we were under the direction from the White House to plan on sending astronauts to this location. And so we selected 3 potential landing sites for astronauts within this basin. And we, looking at the geology of the basin, realized that there were several big questions that they could answer if they collected suitable samples. For example, from the center of the basin, we could collect impact lithologies from which we could determine the age of that impact event. In the walls of that basin, because this occurred in the South Polacan Basin, in the walls we would find impact melt lithologies of the South Polacan Basin from which we could determine its age. And so in this one location, we could determine 2 ages that essentially bracket the entire basin-forming epoch and allow us to address the question of the magnitude and duration of the lunar cataclysm. In addition, there is this mountainous range of rocks. It may be hard to understand, but this is 1 to 2.5 kilometers high, so it's Rocky Mountains in scale. This ring of mountains was uplifted during the impact cratering process from the lower crust of the moon, and it represents some of the crystalline products of that lunar magma ocean that I spoke about earlier. And there's some young craters that provide some incredibly fresh and spectacular exposure. So if we also go to Schrodinger, we can collect these types of samples and test our hypothesis of the lunar magma ocean. Finally, long after the impact event occurred, volcanism occurred in this part of the moon, and it produced some lava flows that erupted over here, and there is a towering pyroclastic vent that erupted over here. And so if we collect this type of material, we can better understand the magmatic evolution of the moon and the thermal evolution of the moon. And more importantly, because at this point in time we are talking about sending astronauts to do this work, there is what NASA calls ISRU potential. That's an acronym that means in situ resource utilization. That pyroclastic vent contains gases that are easily transported, easily produced into bricks and other types of building materials that might be needed if you had any type of long-term residency on the lunar surface. In addition, this pyroclastic vent was produced because volatiles were erupting, and so there is a possibility of a cache of volatiles, which you could then mine for oxygen and rocket fuel. Okay. So at that time, we were planning to send crew to do this. The current administration has canceled those plans, canceled the production of the lunar lander, and canceled our plans to send crew to the lunar surface. So we have moved on, but before I do so, I just have to say this. The best way to do the geology is with well-trained crew. There's just nothing better than a good field geologist. Okay. But we have been asked, now that we're not sending crew to the lunar surface, what can we do robotically or with human-assisted robotic elements? And we've designed two types of missions. One is a lunar L2 Farside mission, which involves crew in the Orion crew vehicle. This is a short 14-day mission, and we've designed to traverse and sample sites where the rover would collect material and then return it to orbit where the astronauts would pick it up. We've also done an investigation of something called the Heracles concept, and this is a mission where the rover would spend 3 to 4 years on the surface and send 3 to 4 packages of rocks into orbit where the astronauts would pick them up. Here is a timeline that illustrates what we have in mind. There's a series of precursor robotic missions that our country and Russia and Europe and Japan and India are planning to do. This human-assisted sample return mission that we spoke about on the last slide is something that we're looking to do in the mid-2020s. And eventually, we do really hope to get humans back to the lunar surface, but that'll be at about 2030. Okay. Here is a diagram that illustrates what we would do. We would launch astronauts in the Orion vehicle. They would hover above the lunar far side where they could communicate with Houston while maintaining communication with the robotic rover. From an exploration point of view, this will demonstrate the Orion crew vehicle in deep space with a high-speed Earth re-entry. This will be a 30 to 35 mission into translunar space. Crew will travel 15% farther than Apollo and spend 3 times longer in deep space, and they will have an opportunity to practice teleoperation of rovers on the surface, which is something that we consider a Mars-forward technology. From a science perspective, we'll get to land on some location like the Schrödinger Basin. Geologic measurements will be made in situ, samples will be collected and returned to Earth. And we also hope to do some astrophysics on the surface as well. So, I have a little movie that illustrates this, if you'll give me just a moment. Get out of this. And again, as I show this video, I'm going to simply let you watch. That's how we'd like to get our samples back to Earth. Okay, now, I've been speaking about the moon, but of course, all of the impact history that I've just been describing on the moon is of course occurring on the Earth. Here's a graphic that one of my postdocs produced that shows all of the impact events that were occurring on the Earth at that very same time. And you can see from this, there's not a single centimeter on the Earth's surface that was not affected by an impact event. And that's something that geologists in general just do not appreciate. I oftentimes go to meetings where they talk about the beginning of plate tectonics, and nowhere in these meetings are they evaluating the effect of some of these 5,000 kilometer diameter craters that are occurring on the Earth's surface at the same time. And as I said earlier, we have this question in our mind, did this impact, flurry of impact events have something to do with the origin of life? Okay, we do know from some work that Kevin Zonley and Norm Sleep did that when these basin-sized events occur, they have the capacity to vaporize any water that was on the surface of the Earth at that time. So if there were seas, they were vaporized. In fact, there was a rock atmosphere for periods of about 1,000 years. And so surface conditions were episodically completely untenable for life. But interestingly, based on some work that we've been doing at Chicxulub, we know that these same impact events have been creating vast subsurface impact-generated hydrothermal systems that were crucibles for prebiotic chemistry and suitable habitats for the early evolution of life. And so we are wondering if, in fact, life began beneath the floor of an impact crater. Okay, so again, to go over that, the largest impact events would have vaporized seas. Conditions on the Earth's surface would have been untenable for life, yet those same systems generated vast subsurface hydrothermal systems beneath the floors of these craters. And those systems would have been ideal habitats for the earliest microbial life on our planet. And I also want to point out, this last bullet constantly gets lost. People think when we spend money on spacecraft missions to other planets that we are putting money on the end of a rocket and throwing it away. Nothing could be further from the truth. Of course, the money stays right here in Houston or some other city in the United States. But moreover, when we go and study some planetary surface like the moon, we are inevitably teaching ourselves more about our planet. In this case, studies of the moon have led to a better understanding of an early epoch on Earth. Okay, now why might we think these impact-generated hydrothermal systems have anything to do with the origin of life? And this is where I turn to my colleagues in the biological community who have looked at the tree of life. They tell me that when they look at the ribosomal RNA characteristics of these organisms, that they had a common ancestor or they had a community of ancestors that thrived in thermophilic or hyperthermophilic systems, that is, hydrothermal systems. Traditionally, those were thought to be volcanically driven systems, but we've pointed out that these could very well be, instead, impact-generated systems. Okay, so as I said a moment ago, our thinking about this has been affected in some part by the Chicxulub impact crater because we have drilled into it. And for those of you who are really interested and know something about hydrothermally altered rocks, I do have a sample that we recovered from this impact crater that has been nicely hydrothermally altered. This is, of course, a crater that is known for the demise of life, not providing clues about the origin of life. This is the impact crater that has been linked to the extinction of dinosaurs and most life on Earth 65 million years ago, but is also a proxy for impact events earlier in Earth history.